Hi everyone. So in a couple previous videos I showed how to start building a balancing robot and built the chassis and modified a couple servos for continuous rotation. And the next step in building this balancing robot is to get a couple sensors working with it so that we can measure the angle of the robot, its orientation. And to do that I ended up getting a neat little 10 DOF or 10 degree of freedom module from ICStation, and this video is going to cover how to interact with it and read the sensor values. So it's a very small little module, and it has 3 different chips on it. It has a chip that is a combination 3-axis gyroscope and 3-axis magnetometer. It has a 3-axis gyroscope and a 3-axis accelerometer. It has another chip that is a 3-axis magnetometer, and it also has a chip that is a barometer, which will measure air pressure and temperature. So it's a very simple, very small module to work with. You use I2C to communicate with it, and basically you need to give it power, so 3.3 volts in ground, and then you have serial clock and serial data for the actual communication. And then there are 2 interrupt pins. Int A is used by the gyro and accelerometer, and then DRDY, or data ready, is used by the barometer. So let's go to the computer and verify this module works and see how difficult it is or how easy it is. It's actually really easy to work with. Alright, so we're back at my PC now, and let's start just by showing you the end result. So I'm going to go ahead and so if I debug my program and get it running, we have our sensor measurements. So right here are the values that are coming from the module. So I actually have it reading at about 70 times per second, at about 70 hertz. But because of how I'm sending text to the computer, it's only updating a few times, but it's actually really quite fast in the microcontroller. Anyway, so yeah, we have measurements of acceleration in 3 axes. We have the die temperature of the gyro and accelerometer. We have the angular velocity from the gyro, also in three axes, and then magnetic field measurements in 3 axes. And so we can verify that the sensor is working correctly. Let's start with the accelerometer. Well, actually, first I'll wiggle the board kind of fast, so we can see everything's kind of moving around, everything's changing. Now let's see if it's actually working correctly. So if we hold the sensor module flat, so it's like parallel with the surface of the Earth, we see that the z acceleration is approximately 1 g, which is good. That's what it should be. Basically one unit of like Earth's gravity. And then if I hold the module on one of its edges, stand it up vertically, we see we now have about 1 g on the x-axis. And if I hold it on the other edge, like that, we see we have about 1 g. We have about 1 g on the y-axis. And then the temperature is the die temperature. It's not going to be your room temperature. So I'm currently in a room that's about maybe 22 degrees Celsius, but the actual sensor is going to be a little bit warmer. So that is normal. That's fine. And then for rotation, if I rotate the board in one dimension, we have our x, primarily a response on the x-axis. In another dimension, we have primarily the y-axis moving. And then the third dimension, we have primarily the z-axis moving. And yeah, that's good. For the magnetic field, if you just kind of hold the sensor module flat, parallel with the Earth, if you just rotate it, you'll see the readings change as you go. And then if you get it near a strong magnetic field, you'll see the readings will very quickly saturate. So if I move it near my tablet, which has a magnetic cover on it, you can see that we're pretty much railing that y-axis, and if I rotate it, the other axes respond accordingly. And yeah, so if you have it under a very strong magnetic field, you can end up getting weird issues like this, where you're getting like a 0, which yeah, because you're basically railing the inputs, and it's not going to give you an accurate value. But if you then move it back away and let it sit, it will very quickly give you accurate measurements again. Alright, so there we have it. We know that our sensor module is working correctly, and we have measurements, and they are formatted. The acceleration is in units of Gs, temperature in Celsius, rotation in radians per second, and the magnetic field in Gauss. Okay, so that's great. How did I actually make this work? What code did I use? Well, I wrote the code myself, and I'll walk you through it. So I'm going to go ahead and stop that. Okay, so first of all, what module am I using? I got a 10 DOF, or 10 degree of freedom module, from ICStation, and they make looks like 3 different versions, and I got this first one. So this has a MS5611, which is a barometer. It'll measure the air temperature and air pressure. It has a HMC5883L, which is a 3-axis magnetometer, and then it has a MPU6050, which is a 3-axis gyroscope and a 3-axis accelerometer. And so the first thing you kind of need to figure out is how to communicate with the devices, and so you want to find the data sheets. So if we search for those, so the MPU6050 again is the gyro and accelerometer. It's a very common one, very easy to work with. And it's made by InvenSense, and if you go to their webpage and if you scroll down toward the bottom, or I guess actually toward the middle of the page, they have the data sheet, and then they have the register maps and descriptions. Both of them are very important, and let's see if we can bring these up. All right. So we'll start off with the data sheet for the MPU6050, and it has a lot of stuff that you could skim through, but it's not really fun to read. But they kind of highlight the features. They highlight abilities, like obviously with the accelerometer you can change the sensitivity, so you can have it be 2G, 4G, 8G, or 16. That's one of the things we'll need to change. Likewise, the gyroscope is adjustable as well. You have 250, 500, 1,000, and 2,000 degrees per second. But yeah, the data sheet is, obviously it'll have specifications, but it's really more of like a, I guess like a glorified advertisement. It kind of tells you what everything is, or it tells you about everything that's possible, but it doesn't tell you how to do any of it for the most part. I mean, it'll cover like, how I2C works, but it doesn't actually tell you anything about the registers and stuff like that. So what we need would be the actual register map and descriptions, and that is the more important file. And so we'll see that there's quite a few registers, all of these, and all of these, and all of those. And then, so if you scroll down, it'll start talking about each register and what the various bits mean, and how to work with them. And so you can read through that, but again, that'll also get kind of boring. And so I'll show you the code that I wrote and walk you through how that works. All right, so there is the gyroscope and an accelerometer. What about the magnetometer? So that's the HMC5883L. All right, so we'll bring up the data sheet for that, and this one is nice. It's just one file, and it has pretty much everything you need to know. So about page 11, it'll start talking about the registers, and there's only looks like 13 of them, so it's pretty easy to work with. And I'll show you the code that I wrote for that. But yeah, same thing here. They kind of go through each register. They tell you what the bits mean and what they correspond with. And so that's good. You'll want to save that data sheet and skim through it. And if we go back, finally there is the MS5611. So if we search for that, so if we go to the first link, that is the manufacturer's website, and then you click on the datasheet link here. All right, and then so same thing, this one also just one document that you really need to keep in mind, and you know, typical datasheet stuff, and then we get, okay, here we go. So they kind of cover like the, I guess you could say the algorithm that you would need to use if you want to determine the altitude. And to get altitude, you need to know the measured temperature, the measured pressure, and you also need to take into account the calibration factors that the factory stored inside the sensor to kind of compensate for the various, well, for variation. And then there's only maybe a dozen registers. They're right here. And yeah, so it's a very simple interface. Basically, you issue a command, which could be like reset or convert D1, and then you wait a little bit, and then you read from the ADC. And again, yeah, so reading the data sheet can get kind of boring, and I'd recommend you skim through it, but I'll show you what I wrote. So that's how you get all the data sheets, and let's go ahead and take a look at the code that I wrote. So pretty much everything is in one file, main.c. I wrote it for an STM32F0 microcontroller, and obviously you may use something different, which is fine. So I wrote it to be fairly straightforward as far as what I'm doing, so you can easily port it to your own microcontroller. But I'll start by walking you through from the beginning. Alright, so for my microcontroller I have to include a basic header file, and then I have a library that I've written over the years that's not terribly good, but it works. And I have an I2C file, a GPIO file, and an external interrupt file that I'm working with. And then in order to get, oh, well, yeah, I unplugged the USB cable, so yeah, it overwrote. But yeah, so the text that you saw here before I unplugged the USB cable, in order to get that to show on the screen, I use a method called semi-hosting, which lets you send text from the microcontroller to the PC through the programmer and debugger. And so that's what these files are for, or these lines are for. You won't need those most likely, but I included that because I wanted to show you guys the sensor readings. Alright, so you will need values to store your measurements in, and it's easier if they're globals, so I made them all global here. And I just called them, like the first part was the sensor, so accelerometer, and then the axis, and then the unit, so G's, Celsius, radians per second, Gauss. I didn't bother converting the pressure and temperature of the barometer, mainly just because I didn't actually use that sensor for the balancing robot, so I didn't bother going to that trouble. Alright, when you do I2C communication, you have to specify the device address, which is a 7-bit value, and I define those here. So the MPU6050 is the gyro accelerometer. The HMC5883L is the magnetometer, and the MS5611 is the barometer. And then, as we saw in the command line window, we had a bunch of graphs for all the values, and I wrote this function that basically does that for me. So the first argument is name, which you'd give it that string or whatever you want to put on the left, and then the value is this number, which is shown here and then graphed here in the middle. The unit is just printed here, and then min and max set the range of the actual graph. All right, so yeah, here's the function. It's pretty straightforward, but you really don't need to worry about that because, again, this is just for demonstrating it in the video. You wouldn't actually be printing all that information out in your actual robot. So we get to main, which is where we start execution. And again, I have to initialize the semi-hosting code, and basically I initialize the code, and then this line makes it so that it will buffer until I manually flush the buffer. And that just makes it a little bit more efficient. If you don't put that line in, anytime you have a new line, a /n, it will flush the buffer. And there's some overhead in that, so if you do that too frequently, it'll slow things down quite a bit. But again, you don't need to use this most likely. Okay, so what you will need to do is you'll need to configure your I2C peripheral. And the function that I wrote for that, I tell it to use I2C peripheral number 1, and I want to use a 400 kilohertz clock, and then the clock pin is PB8 and the data pin is PB9. And then you're also going to need to obviously configure the devices. So the first step is right here. We want to configure the MPU6050. Now at power up, it's going to start off in sleep mode, and you want to exit that so that way you can actually start making measurements. So you go to register 6B and you write a value of 0, and that will exit sleep mode. And so likewise, the rest of these, the register number is here, the value is here, and so on and so on. I configure a sample rate of about 72.7 hertz. The balancing robot that I'm designing, I'm going to have it do all the math and apply new values for the motors every time I get an input from the sensor. So I configured it for a reasonably fast value. I wanted a little more than 50, but I didn't need more than 100, just because you can only respond so quickly with physical motors where you have momentum and stuff like that. So I picked a value of about 73 hertz. You can pick whatever you want. The maximum is 1000 for the accelerometer and 8000 for the gyro, and they're all based off the same prescaler, and that's all covered in the data sheet. And then by default, the gyro range is really narrow. It's the 250 degree per second value, I believe. And because the robot is fairly quick, I wanted to have it be able to sense quicker rotations, so I used 2000. And then same for the accelerometer, it'll default to about plus and minus 2 Gs, but I found that to be pretty close to the edge. I didn't want to have it rail the measurements, so I pushed it up to 4. And then finally, I wanted to get a interrupt whenever the measurements were done. So basically at 73 hertz, I want to get an interrupt, and I enable that here. All right, so now we have a magnetometer, the HMC5883L, and on this particular board, instead of being wired directly to I2C, it's actually wired to the gyroscope and accelerometer. So what we need to do is we turn off I2C master mode in that gyro accelerometer, and then we enable master bypass mode. And what that does is it will basically connect the magnetometer direct to the I2C lines. And so those two commands go to the gyroscope accelerometer. And now that we've told it to pass all communications to the magnetometer, now we can actually talk to the magnetometer, and we write 3 registers. First one, I set the sample rate to be 75 Hertz. Again, because I wanted it to be roughly in line with the gyroscope and accelerometer. I set the full scale to about 2.5 Gauss. And then continuous measurement mode just has it free run and keep on making measurements as opposed to just doing one at a time. So that's pretty much all you have to do to configure it. So now we go back to telling the gyroscope and accelerometer disable bypass mode and enable master mode. And so now we're back to where the gyroscope and accelerometer has control over the magnetometer instead of us. And so it has control over it, but it doesn't yet know how to read from it. So that's what we do here. So we write to a register, we tell it the address of the magnetometer, and then we set the most significant bit, so that which would indicate we want to read from it. And we want to read from register 3. We want to read 6 bytes because we have 3 axis measurements, and each measurement is 2 bytes. And then we set the most significant bit, which will enable that that channel, that control of the magnetometer. And then finally, I have slave 0 delay, which means that the interrupt will be delayed. This one right here, we delay that until after we get our magnetometer reading. That way, when we do a read from the MPU6050, we can read everything out all at once, and it's all ready, and we have the most recent values. So here I show how to configure the barometer, but I didn't actually, I commented that code out because we really don't need a barometer for a balancing robot, but I'll leave it in the code so that if you want to play with it, you can. And then, so like I mentioned earlier, the MPU6050, we get an interrupt on the int A pin, and I tell my microcontroller that it's an input pin, and I want to get an external interrupt on a rising edge of that pin. And then likewise for the barometer, there is a DRDY or data ready pin, and if you want to use the barometer, you could do the same for that pin. Okay, so this was the part that we saw earlier where it drew the graphs and that we saw. So again, you wouldn't need to use this code because you know, when you're actually making a robot, you don't need to print all those values out, although you could at the beginning to verify everything works like I'm doing right now. So I call that print graph function that I wrote up here for each of the values, and at the very end I have this kind of weird looking line if you've never seen it before. So this is called a VT100 escape code, and what it does is it lets you control where the cursor is. So yeah, again, so I unplugged the cable so it looks all weird here, but you know how normally there's like a cursor where like one line or one thing will be like selected? Well, you can actually move that cursor. So you can move it up or you can move it to the left or to the right. And so /x1b is the hexadecimal code for the ASCII escape character. And an escape character is a non-printable character that will let you basically give a command to the terminal, which in this case is, you know, this program, this, geez, what is it? I don't even know what it's called. I'm using min-tty. It came with Git for Windows. And so, yeah, we basically send a command to the terminal, and the command is a opening bracket followed by a number followed by a capital A. And that sequence will let you move the cursor up by however many lines you specify. So I move the cursor up 14 lines because I have 14 lines right here. And so if you're interested in kind of how that works, just search for VT100 escape code. And yeah, there's a lot of them out there. Keep in mind that not all of them will work on a modern computer. and not all of them will work on every terminal. So again, I'm using MinTTY, which came with Git for Windows. But if you use like cmd.exe or some other terminal, it may not work. So just keep that in mind. But yeah, the whole reason for why I did that is I wanted it to draw those graphs and then draw over them. So if you don't do this, it'll just stream text by really fast. It'll just kind of flood the screen and you won't be able to read it. Whereas if you move the cursor up and then you write your next batch of values on top of it, it'll work the way I showed you. Okay, so that's kind of the end of main. And what happens now is whenever we get an interrupt on int A, we'll get that external interrupt that I configured over here. And that will take us over to this interrupt handler. And so this is specific to the STM32F0, so yours is going to be a little bit different, but basically whatever code you need to do to get an external interrupt working, just do a little bit of research. There's plenty of documentation, I'm sure, for whatever microcontroller you're using. And on mine, I have to check for the interrupt, and I check for the interrupt on pin 7. And then I clear the interrupt to tell the microcontroller that I'm handling it. And then I read, or I call this function that will read the MPU6050. And that's this function right here. And this function does all the work. So we start off by creating a buffer. I create a 20-byte buffer. We then want to read from the MPU6050. We want to read 20 bytes. We want to start at register 3B, and we're going to read them into our buffer, which is right here. After this line is done executing, we now have our 20 bytes of data, and that has our accelerometer, temperature, gyroscope, and magnetometer readings. But we need to turn those bytes into numbers, and all of these sensors give us a 16-bit signed integer. And I do that conversion here. So we create a 16-bit signed number, and you give a name for each one of them, and then you tell it which byte goes where. So byte 0, the first byte that you get, is actually the most significant byte. And then the second number you get, which would be 1, is the least significant byte. So we do some bit shifting here. We shift that first byte to the left by 8 to push it into the most significant byte location. And then we do a bitwise OR with the least significant byte. And we repeat that, so byte 0, 1, 2, 3, 4, 5, and so on, all the way through 19. And those are our values. And again, because we have our magnetometer being controlled by that gyro accelerometer chip, it's all part of one read, so it's really convenient. We just do one command to read. Okay, so now we have our sensor readings, and we have them as signed integers, but I wanted to show them as floating point numbers with units that would be more meaningful to humans. So I convert the accelerometer readings into G's, and the datasheet indicates how, and so basically you divide by 8192, and that'll give you the number of G's. Likewise for temperature, the datasheet will tell you the numbers you need to use. There's a scaling factor and an offset, and that'll convert the integer into a floating point number for Celsius. For the gyroscope, they tell you in the datasheet the scaling factor for degrees per second, but I actually wanted radians per second. And I wanted that because in the next video where I show how to do sensor fusion, the algorithm that I use requires radians per second. So you can Google how to convert from degrees per second into radians per second, and the end result is you divide by 939.65 and so on, and that will give you radians per second. And then finally, we want to convert the magnetometer readings into Gausses, and the datasheet covers that scaling factor as well. So that's really it. That's pretty much everything we needed to do. This other function is for the barometer, which again I'm not using because I don't need that for a balancing robot, but I'm going to leave the code in here so that if you want to, you can look at it. This code just reads the raw values. It doesn't actually apply those calibration corrections or convert those pressure and temperature readings into altitude. But there is plenty of documentation in the datasheet and online telling you how to do that if you want to. So yeah, this entire project was 230 lines. It's very easy to work with. I've had pretty good luck with this this sensor module from ICStation. It's working pretty well. So yeah, it's a 10 DOF or 10 degree of freedom. The module name is GY-86, and yeah, in the next video I'm going to show how to use sensor fusion, which is a way to take all of these measurements and accurately determine the orientation of the robot, so the angle, if you will. And so stay tuned for that. I should have that posted pretty soon. Hope you liked the video. If you have any questions or comments, please leave them down below. If you know anybody that might benefit from it, please share it with them.